thinking about what's left in the semester. There's one more assignment, I believe. That is just the internal loads problems. And all assignments are must be in by if you're turning in hard copies, that's Friday, a week from tomorrow. If you're doing PDFs, I have to make a Dropbox for that, but you'll see it on D2L shortly. Then you can go up until 1 full second before midnight on Sunday night, okay? So if you get it in at 11:59 and 59.6 seconds, then it's late, okay? It has to be a full second before midnight. So that would be 12, 11, 11:59, 59.0, okay?
And that's like the world clock?
Let's see. Yeah, that's central. But yeah, that's going to be based on the atomic clock, the Colorado one, okay? The Colorado atomic clock.
Just want to make sure.
Yeah.
Sometimes my
Yeah, because if you're looking and you just look at your watch and you're like, oh, I got plenty of time. I still got like 43 seconds. But, you know, I'm going to watch a little more Seinfeld before I submit this.
Well, it's like trying to win that bid on eBay.
Yeah, exactly.
Very last second.
You can just slide it under. Yeah, I don't have a basket on my door, but just slide it under the door. And so, yeah, feel free. Anything you don't have in yet, get it in, and I'll give you full credit for it. Okay? I mean, if it's good. Which, yeah. And then, what do we have left? Did we take a quiz? Do we still have a quiz? On Tuesday, okay. One more quiz on Tuesday. And the one more assignment thing. There's one more assignment, but there's also one more set of things that you're responsible for the test. You just don't have to turn them in. So you need to work through the friction problems. That's just not going to be submitted, but that's going to be on the last test. And then exam 5 is Thursday, 12:15 at 8 a.m. Yes.
Just have like question. What happened like if something happened like there was really snowing outside and car stuck, or because I'm always nervous about this, like
Yeah.
just like
If I were you, I would just bring a sleeping bag on Wednesday. Yeah. Just, I'll bet you can find a place in like the activity center where they don't look. It's not allowed, but I'm sure you can find somewhere to hide. Yeah. I don't know. I mean, I'm sure that they do have snow days, but I don't know. We've been pretty lucky so far this year, so.
That would be the day, a snow day on finals week.
That would be a disaster. I've been here 8 years, 8.5 years now, and I've never had that happen. They don't close the school very often, you know.
Like, we never have snow days in Minnesota.
No park in the park ramp.
Yeah.
That closes a half hour after.
Yeah, right. I bet you could find, like, there's lots of nooks and crannies in the library. I bet you could find a place you could just huddle until the security had left.
Just
Right by the engineering books for no one goes.
Actually, if you want, you can stay in my office. So anybody who wants to stay overnight Wednesday night, just come by my office. I have a night class, so you have to be there by about 9. Okay.
Well, all night.
Yeah, it'd be like a lock-in. Yeah, sure. Breakfast, continental breakfast. Yeah, right. Yeah, you will have to do some work, like some laundry and stuff. We're gonna run like a little sweatshop, one night sweatshop.
Clean the desk and
Yeah, yeah, exactly.
Can you give us your login information to watch Park Solar Trail?
Yeah. All right. Any questions about any of the rest of the semester? Okay. There's one problem correction. I think it was number 6 in internal loads. It looks like you have these two members crossing. I don't remember a lot of details of the problem, but it doesn't give lengths and it doesn't give angles. So use the lengths being 1 meter, and the angles are both 10 degrees from the vertical. So, this angle is 10 degrees, and this angle is 10 degrees. Oh, okay. Do you happen to know what weight I used in the solution?
Yeah, 400 kilograms.
Okay. It's just a single beam. So the mass of the beam is 400 kilograms. That's a really heavy beam. Yeah, exactly. So, I mean, I guess what that means is that it extends into the page, most likely, you know what I mean? Like you could have a wider plate or whatever made out of steel that could weigh that much. Yeah, but it gives it a length and stuff.
Yeah, it's just a 1 meter beam that weighs 400.
1 meter. So it has to extend into the page, exactly. Or be made out of neutron star or whatever. Okay. Any questions about problems, assignment problems, or so all we have left to do is friction, and that shouldn't be too hard to get through in 3 classes. So yes. Yeah. Anybody have it sitting in front of them? In internal loads? A is the one where it just okay, so there's a pin joint on the right side. A roller on the left side, and a rectangular distributed load all the way across. And there's no weight. The length is 3 meters. This is 10,000 newtons per meter. The first thing you have to do is calculate the external loads. So if you think of this distributed load as a rectangle with a height of 10,000 and a width of 3, not drawn to scale, and the total area is 30,000 newtons. The centroid's right in the middle. So a free body diagram of the whole thing. At the pin, we have a full force vector. At the roller, we have a force pointing up. And then at the middle, we have a downward force of 30,000.
Is it just safe to assume that that roller is right on the end?
Yes. So now you can write out the table, or we could also, for these horizontal ones, it's not too hard to just think through what's happening. So that's what I'm going to do. But with any rigid body problem, you can always write out that table if it helps you, including, when you do those cuts, each one of those is a rigid body problem, and you can write out the table for those if you want to. This is sort of a shorthand. I'll put the about point here for the external loads. So Newton's second law says 0 RA plus 0 negative 30,000 plus RBX RBY is equal to zeros. And the moment equation, there's no moment produced by RB. The 30,000 has a moment arm of 1.5. And would that produce a clockwise or counterclockwise moment around this hinge? Counter, so that's positive.
Wouldn't that be negative 1.5 with our coordinate system?
Because don't think of the coordinate system, if you're doing it shorthand like this, if you're just doing this by sort of inspection, don't think of the signs of these values. Just think of magnitude, and then do the sign based on the rotation.
Okay.
And then RA has a moment arm of 3. And would that produce a clockwise or counterclockwise rotation? Clockwise, so that's negative. So RA is 15,000. So RB is 15,000. Well, actually, I should have been able to see that. That's all just because of symmetry. Those have to be the same, and they have to each take half of that load. And so the vector RB is 0, 15,000. Okay, so now the biggest danger to screwing up the cuts is that the last picture you drew is trying to mislead you about where to make your cuts. You know, you look at this picture and you think endpoints and a point force in the middle, so that's n equals 3. You need 2 cuts, but that's wrong. This force in the middle is not a real force. That's a mathematical thing that we use to solve the problem. So the real answer for how many cuts you need comes from the picture, or it comes from a free body diagram before you treat that distributed load as a point force. And so based on this, we have the 2 endpoints. The distributed load function never changes, and so n is equal to 2. We only need 1 cut. That 30,000 Newton force in the middle isn't real. Okay, so our cut is valid for all x values. And I'm going to draw this in 2 steps. Yeah, because that point force, there's not really a point force applied at the middle of this beam. There's really a distributed load. And so each time we choose a new cut, we have to treat this as a distributed load.
So is it all over the beam, or we choose it to be at point force, but in reality the distributed load is all over the beam?
So, right, it's all over the beam, and so we only go from the distributed load to treating it as a point force once we've chosen the cut, once we've chosen what body to isolate, which means every time we go to a new cut, we have to think of it as a distributed load again and recalculate what that point force is.
Okay.
Yep.
This is kind of piggybacking on the structures, right? When we were kind of coming up with an overall force, but typically that force is kind of prorated, or at least averaged along those given intervals in which we were calculating for, correct? So if you had something like 15,000 Newton meters over, let's say,
Yeah. Yes.
you have 3 points at 5. Let's say if you had theoretically 3 points, well, that would be theoretically 5,000 Newton meters at each point.
Yes, that's right. Yes. Yep. Okay, so for the first cut, we're ignoring all the stuff going on here. You know, there's all this beam that we're not considering, and that beam includes part of that distributed load that we're not considering. We're only considering this piece and this piece of the distributed load. Since this is a constant distributed load, a rectangular distributed load, the magnitude is 10,000 newtons per meter. We have an upward force from the roller of 15,000. And then we have the internal loads. And now that we've chosen a body to isolate, let me, so this point here is x equals 0. This point here is some arbitrary value of x that has to represent any choice between 0 and 3. So now our distributed load looks like this. This rectangle has a height of 10,000, a width of x, The centroid's right in the middle, or in other words, x over 2 from either end. And the area is 10,000x. So now I'll redraw this. We have a downward force of 10,000x. Newton's second law says 0, 15,000, plus 0, negative 10,000x, plus t negative v is zeros. So there's no tension. V is equal to negative 10,000x plus 15,000. And then the moment equation, our about point is over here, like always. So the 15,000 doesn't produce a moment. The 10,000, what's the moment arm for that 10,000? X over 2. Anyone have any questions about that? The magnitude of the force is 10,000x. Is that clockwise or counterclockwise? Clockwise, so negative m. Yeah, because it's a new about point now. M minus Vx is equal to 0. So m is equal to Vx plus 5,000x squared. Substitute in V here, and you get negative 10,000x squared plus 15,000x plus 5,000x squared. When you add up the negative 10,000x squared and the positive 5,000x squared, you get negative 5,000x squared plus 15,000x. Do the derivative checks. dm dx, negative 10,000x plus 15,000 equals v, so that one works. And then dv dx is negative 10,000. Negative dv dx is positive 10,000. And that's the q.
We choose x as a length, just like arbitrary length between, like, we choose it in the middle, but now we choose it any length, like any length between.
Right, it has to represent this whole interval of lengths. In between, a whole interval of lengths in between those key points.
Yeah, like 0 and 3, but it
Yeah.
could be any length,
Yes. So what this says is that, well, I don't I don't even want to have the internal loads for the whole thing. I only want the internal loads at x equals 2.4. And so then you plug 2.4 in for x, and it gives you the internal loads at that point. And if you go back to the first example we ever did, we didn't, before we started representing these lengths as x, we just chose a value and calculated the internal loads. If you did it that way, didn't do it as x, just did it as x equals 2.4, you'd get numeric values, and they would match what you get from these functions by putting 2.4 in. Yes?
Where the x over 2 came from?
That came from the centroid. So this is x equals 0. This is x. The centroid's right in the middle, so it's like the average of those two values, so x over 2. You know, either one of these two distances is x over 2. Any other questions about that one? Any other internal loads questions? Yes? Yeah, so 3B, the beam is cantilevered on the right. That's what we always like to see because it means we can be lazy about calculating the external loads.
So just a quick question.
Yeah.
The last example, when you say calculate the PV and M diagrams, is that
Oh.
what we're looking for? Is just,
Then plot them. Plot those.
okay, because then like the next,
What does it say?
then the next.
Oh,
one says
calculate.
Graph them.
Calculate. Actually, yeah, that's a little, that wording is weird. Like, do you want us to calculate those functions or draw the diagrams? Whichever one you want on that one. The wording isn't good. You don't have to do the diagrams for that one. Do the diagrams for the ones where it says graph it out. But don't do it by hand. That would be insane. Just go to like Desmos or use Excel or something and plot those. You know, use a plotting function to do that. I don't have it in front of me. What about it?
But like 3A, B, and C said to calculate.
Yeah, so any that say calculate, just do the functions, that's fine. The ones where it says plot a graph or graph the functions or whatever, give me the graphs on those. But yes.
I have a general question about, so we're gonna go over, what is it, internal loads today, and then we'll have a quiz Tuesday, and then Thursday, the last day before exam. So we're gonna do probably a little bit of internal loads on Tuesday, and then friction on Tuesday and Thursday?
We're done with internal loads.
Okay,
So the next new stuff I'm going to talk about is friction.
okay, so we'll do that. So on Tuesday, our quiz will be from internal loads that.
Right,
Right, okay, and then we'll learn about friction Tuesday and Thursday.
right.
Do you have office hours? 5 to 2?
I'm going to just keep I think my usual ones are work pretty well when based on like my final schedule. So let's just keep the same ones. So Monday 3 to 6, Monday 3 to 6 in the lab, next 24. Tuesday 1 to 2 in my office because the lab isn't open then. And then Wednesday 5 to 6 in the lab. All right, so this distributed load is 25,000 newtons per meter. We have a force vector. If you calculate the components of that force vector, it's positive 17, 600? 677. Negative 17, 677. And then these lengths are each half a meter. Well, we can right now figure out how many cuts we need to do. So there's the two endpoints. And then in between the two endpoints, are there any point forces? No point forces. Any places where the distributed load function changes? This one, that distributed load does change at the middle. So n is equal to 3. And so we're going to need 2 cuts. And like I said, we can skip the external load calculation and just go right to the cuts. So cut 1 is for x values between 0 and 0.5. So we're leaving off a whole bunch of beam, and we're leaving off the entire distributed load. all we have acting are the point force on the left and the internal loads. So Newton's second law says 17,677, negative 17,677, plus T negative V is equal to zeros. So T is equal to negative 17,677. V is equal to negative 17,677. The moment equation, the about point is at the left, so all we have is plus m minus vx equals 0. So m is equal to negative 17,677x. M is equal to Vx, and then V is negative. And these are valid on the interval x between 0 and 0.5. And then the second cut is valid for x values between 0.5 and 1. We're leaving off some amount of beam like that. And so we have the force over here at the left, 17,677, negative 17,677. We have the distributed load of 25,000. And then we have the internal loads. And now that we've made the cut, we can treat that rectangular distributed load as a point force. It has a height of 25,000. Its width is a little, you have to think about it a little more this time. This whole distance is, okay, so let's think about these locations. This is x equals 0. This is x equals 0.5. And this is x. So what's the distance, what's the length of this rectangle? X minus 0.5. And the centroid's in the middle. So now, what's the distance between, so if the centroid is here, what's the distance between x equals 0 and that centroid? That's right. So there's two ways, I think, that make sense to think about it. One is that, where you think it's 0.5 plus half of that length. And the other way, the way I like to think about midpoints is just average the 2 points, you know? So the average of 0.5 and x. So this length then is 0.5 plus x divided by 2 and the area of that rectangle is 25,000 times quantity x minus 0.5. That's 25,000 x minus 12,500. And I'm going to rewrite this one as 0.5x plus 0.25. So now I'll redraw this piece of beam. We have the force over here, 17,677, negative 17,677. And we have the point force that has a magnitude of 25,000 x minus 12,500. Where this distance is 0.5x plus 0.25. And then we have the internal loads. And you're going to have to distribute out these polynomials when you calculate the moment, because you're going to have this, moment arm there, this force there. But I think you're up to it. Remember that, FOIL? FOIL? Okay, good. So Newton's second law says 17,677 negative 17,677 plus, okay, so now this is a magnitude. You can see this is a positive number and it's pointing down. If you get confused about, like, is that a positive or negative number, plug in a value of x, okay? So that's a positive number pointing down, which means we're going to multiply this magnitude times the unit vector 0, negative 1, which means that we have the opposite of this in the negative y direction. I mean, the opposite of this in the y direction. So I'm going to write it as positive 12,500 minus 25,000x. Plus t negative v. So t is equal to negative 17,677. V is equal to negative 25,000 x plus 5,177. Oh, yeah. And then the moment equation. This is our about point. No moment produced by the force on the left. But then we have this ugly thing. It has a moment arm of 0.5x plus 0.25. The magnitude of the force is this, 25,000 x minus 12,500, then plus m minus vx is equal to 0.
So it's clockwise.
Oh, yeah, I didn't think about that. Yep. So, so we have the moment arm, the force, and now we have to think about the direction of that rotation. That would produce a clockwise moment. So I didn't give that the right sign. Okay, that's probably enough. But yeah, so you have to FOIL that out, calculate m. It's just a lot of bookkeeping, algebra stuff. I ain't doing that.
Do we need to find the internal loads for number 2? It says reaction loads.
The idea is the internal loads. If you, it's more practice. It's worded wrong. So if you only calculate the external loads, I won't mark it wrong on your homework. But it's more practice. I think the solution calculates. Do you know? Have you looked at the solution for that one? Okay. So the problem is, like, I rearranged a lot of these problems, and so some of the problems ended up in the wrong problem sets or whatever, little by little. It's a slow, iterative process to iron those things out. So that one was probably originally like a problem for rigid bodies, and it just ended up here by mistake.
Or it might be a problem for rigid bodies and you just forgot to add part B.
Right. One of those two is definitely what happened, yes.
So why we have two cuts? We have distributed load and we have n equals 3, and the other one we have like n equals 2. We have
Because the that n counts up these things: endpoints, point loads, and, well, it's counting up points. And those points add up if they are endpoints, and or locations of point forces, and or locations where distributed load functions change. And so in 3A, that distributed load function never changes. In B, that's the difference. Is I don't know if I drew it. Yeah. So in B, that distributed load function changes at the middle from 0 to Q equal 25,000, and so that's why that point at the middle counts as adds an n.
I was just going to wonder if there's any time you'd ever want to use like a unit step function for something like B, for Q.
Oh, I can't think of a way that would help, but I think that's just a difference in representation. But
So
if you think about it and come up with a cool new thing, I'd love to hear about it. You know.
So it's like distributed load through the whole beam. It will be like we won't count it as a cut.
Right.
But because it's
Yes.
in the middle, it would be like 3/4 or 1/4 of the beam. But then we count it as
Yes. Right. Yes.
It's not really like I don't want you to do a whole question, but on number 8,
Mm-hmm.
it's like they're on an angle. And I'm just wondering a little confused about like the theta being rotated, like
Okay. So remind me, does that one, they're at sort of a shallow angle like this? Yeah, can I see it? Oh yeah, that's not it. It's a triangle. So it's a structures problem. These angles are 70 degrees. You have a downward force of 10,000. Horizontal force of 5,000. So first you go, yes? Oh, in the solutions, which should I do? Okay. Yeah, there's that gap there like it's supposed to be. Okay, well, one more thing. So once you calculate the external loads, you have, and these don't have masses, right? So you end up with, one force down here. I'm going to just call that F1. Once you combine all these forces going on, it's a two-force member. Over here, you have F3, 5,000, F4. Yeah, everything's lumped together. So this is not, these are not the free body diagrams you would use to solve for the external loads. This is just what you have going on after you calculate the external loads.
I have a question. Do we switch the coordinate like system?
Yeah. So for the next step, and that's what she was asking about. So let's call this member 1, this member 2, and this member 3. So for member 1, okay, so for these members, is there anything you could do to sanity check your external loads? On 1 and 3, they need to be equal and opposite, and they have to be parallel to the beam. On 2, there's not as much you can do.
Do you need to include a force from the roller on the wall?
Yeah, I don't know if I should have done the free body diagrams this way. So the idea, my idea when I did this is that 10,000 is lumped in here, the roller force is lumped in here. But what you end up with is external loads that when you add up all the loads acting here and you add up all the loads acting here, you end up with equal and opposite forces parallel to the beam. Same thing here. Those are just space holders, yeah, right.
So F1 and F2 are equal and opposite? Or number 1 and 2?
Yes, you're exactly right. Okay, don't change anything you have been thinking about up until this point based on this diagram. Okay, so member one, we're going from a coordinate system like this to a coordinate system like this. Most likely, although if you wanted to use this coordinate system, you could figure out that rotation.
You said X always goes in the line of the axis of the.
Yeah, the X always goes along the beam. That's right.
Doesn't matter which direction.
It doesn't matter which direction, right. But it always points from your starting, your X equals 0, you know, like your first cut, towards the end of the beam. So if you do it the other, if you do choose to do it with your x-axis that way, that has to be the left end of your beam when you start your internal loads. You know what I mean? Okay, so what's the angle theta for this rotation? Yep, positive 70.
So why is it 70? Did it rotate counterclockwise or clockwise?
Counterclockwise is positive.
Oh, so it rotated counterclockwise.
The coordinate system rotated counterclockwise 70.
Oh, okay.
What all of you, every single one of you is going to screw up at some point in your life is thinking that you want to take this beam and rotate it down like that. Yeah, when you rotate the coordinate system and then you turn your head, you don't rotate the member. Okay. If any of you retire from engineering at 70 or whatever, and you haven't screwed that up at some
You're
point,
optimistic.
let me know. You know. Yeah, let me know. And I'll give you something nice. But you have to. This is something you have to keep fighting against actively, because your brain is going to want to do that. You know, you're rotating the coordinate system, not the body.
So basically, you are putting a system like that, you rotate it to the regular one, or vice versa?
You're going from the regular one to the one with the x-axis along the beam.
Okay, so basically, if you're going this way, you're going like right down. Oh, okay, I see why it's turned this
Okay.
way. This is because I saw the X and Y differences.
Member 3, you don't have to rotate. Member 2, well, which way? You know, you get to choose. I suppose, I don't know. I probably just always do it with the smallest angle I can, but there's no reason that that's any better or anything. So you go from this. You're out. You're out of the running for something nice when you retire.
But you don't remember that you want to take that in, but like to keep it, to remember that, because I feel I'm gonna forget.
Yeah, you are.
Yeah.
Nothing personal, but you are. Okay, so we're doing a rotation like this, and so theta is negative 70. Yep. I don't know. All I can say is just keep reminding yourself, you know. The more you remind yourself, the less it'll happen.
Yeah, because when I told you about that, I saw about the beam, but then I
Right.
remembered that.
Yes.
So,
Yep. Oh. What do you mean cancel out?
Like, if you add, like, it's gonna be, like, one is going that way, one is going this way, so it's going to be static equilibrium.
Oh, yeah, they have to be in static equilibrium even after the rotation. If that doesn't happen, then something went wrong. Can we just talk about that after class or in office hours or something? 'Cause this is just such a long problem. I was thinking like I'll go through it, but it would, this is a long problem to do in class.
So basically, just for the rotation, the x-axis, x direction, we look at the beam and we draw it like the direction of the beam, right?
The x-axis is the direction of the beam.
Okay.
Yep. Any other problems? Let's just keep doing problems. We only have 15 minutes left.
What is there a good one on
You want to do number 9 because that's one where you have to use the rotation matrices and it's not going to be too long. Yeah. This angle is 35 degrees. The length is 1.5. There's a 10,000 Newton force. Whatever. 10,000 Newton force here, down. It doesn't say anything about this contact. That could be frictionless or friction. What are we going to use? Frictionless. Why? It's not just easier. If we treated that like a friction contact, this problem isn't solvable. We only have one rigid body. We only have 3 equations, so we can only have 3 variables. Yep.
By the way, do we know where here is 10,000?
Right in the middle.
So if we just deem that to be friction, a friction contact, we just say problem solvable.
You can do that. I mean, it's a free country, but it doesn't go very well when you do stuff like that.
Is it stated in the problem that it is exactly at the midpoint?
Yes.
Okay.
So when mostly we assume that we don't include friction only when there is like internal load or that
No. If the problem can only be solved with frictionless, you assume frictionless. Okay, so free body diagram. The pin joint in the middle creates a full force vector. The contact over here, now that we know it has to be frictionless, that's just a force in a known direction. And then we have the downward force of 10,000. Let's put the about point in the middle at the pin. So the row vector from the pin to the end is going to be 0.75 times cosine and sine of negative 35. Can someone tell me what that is? 0.75 times cosine and sine of negative 35 degrees. What is it? That's the sine? Negative? Are you in radians? Okay.
Easy know that many grid identities off the top of your head?
I just know the quadrants. 1, 4, and then the y. Okay. The force vector is 0 RB. So the moment is 0.614 RB. RA has no row vector.
Did we don't, we have not start using the row form multiplier?
Yeah, you can. It's a little, you know, when this thing isn't horizontal, it's a little more of a hassle. It's easier when the beam is horizontal. That's when I tend to use it, or vertical too. But when it's at an angle, because then you have to do the trigonometry for each one and stuff. Okay, and then the last one, I guess, is half of this, so 0.307, negative 0.215. The force is 0, negative 10,000. So 3. So that's negative 3,070. Newton's second law says 0 RB plus RAX RAY plus 0, negative 10,000 is zeros. The moment equation says 0.614 RB minus 3070 is equal to 0. So what's RB? Ooh.
5,000?
And then that means RA is 0, 5,000. Okay, so now to do the internal loads, we're going to go from a coordinate system like this to one like this. So what's the angle? Yeah, negative 35 degrees. And so the rotation matrix is cosine of negative 35, sine of negative 35, negative sine, negative 35, cosine of negative 35. What's cosine of negative 35? 0.819. And what's sine of negative 35? 5.7 what? And now one by one, we're going to multiply that by the forces. So RA, we have 0.819, negative 0.574, 0.574, 0.819, times 0, 5,000. Can someone multiply that?
Negative 2,807.82.
Wait, 2,000. Oh, what, I put a 0 in there for no reason. 2,867 point.
0.882.
Okay.
And then 4095.760.
Okay. And then we have the 10,000. As a force vector, that's 0, negative 10,000. And I guess that's going to be whatever 2 times this is. 5, 7, 4, 0, and negative 8190. Round off error. And then RB is this matrix. Times 0, 5,000 again. So negative 2867.88, 4095.76. Okay, so now we have a beam, a rotated beam with a rotated coordinate system. How do we translate that into a horizontal beam with a...
Rotate your
Yeah, right, yeah, turn your head, yeah. Very good. So we have nothing until the midpoint. At the midpoint, we have a force of 2867.88, 4095.76. Halfway between that and the end, we have a force of 5740, negative 8190. That's the round off there is kind of egregious. And then over here we have, oh, I missed a negative sign here. And then the last one is negative 2867.88, 4095.76. These are all actual point loads. None of those are representing distributed loads. So we have n equals 2, 3, 4. So 3 cuts. But each one of those cuts is easy because it's just point forces. It's not going to be like messy algebra or anything.
only only distributed with Gauss-Matty algebra, right? Or
Yes, that's right. Yeah, because you have that Q function that's a function of x, and so you get higher powers of x in everything, and yeah. Any questions about that? All right.